So we're going to look at transformations of logarithmic functions today. So we're going to use the same principles, the same characteristics that we have been using to do transformations of other functions. We're going to see that the same rules will apply to logarithmic functions. We'll also look at sketching some of those graphs. But first, we're going to start by looking and seeing how we can evaluate logs with bases other than base 10, right? But remember that the graph of the logarithmic function in the form y equals a log base c of b bracket x minus h plus k, we can obtain them by transforming the graph of y equals log base c of x. So the parameters that we're working with are the same ones that we did before, a, b, h, and k, where a causes a vertical stretch by a factor of a, and if a is negative, it reflects it over the x-axis. As a mapping notation, x comma y maps into x comma a times y. B causes a horizontal stretch, but remember that the horizontal stretch is a factor of 1 over b. And when b is negative, you get a reflection over the y-axis. And as a mapping notation, x comma y maps into x over b comma y. H shifts the graph left and right. Remember, the value of h is always the opposite of what it appears to be. And so x comma y maps into x plus h comma y. And k shifts the graph up and down. So x comma y maps into x comma y plus k. So same principles as we have been using for other functions. But first, let's see how we can evaluate logs with bases other than 10. So the first question here, bless you, asks us to evaluate log base 5 of 25. So we can do this by setting it equal to x and then changing it from logarithmic to exponential by starting with the base and cycling through. This log has a base of 5. When you write it as an exponential function, its base will be 5. It'll be 5 to the power x equals 25. We've already seen that log base 5 of 25 is really asking 5 to what power is 25? And obviously the answer to that is 2, because 5 squared equals 25. Then it asks us to evaluate log of 25 divided by log 5. So for those two logs, there is no base indicated, which means it's base 10, which means we can use our calculator to evaluate that. We can take the log of 25. Now, when you do this, you have to close the brackets after the 25. So it only takes the log of 25 and divides that by the log of 5. And when you do that, you also get an answer of 2. So this tells us that log base 5 of 25, which equals 2, will be equal to the log of 25 over the log of 5. They're both equal to 2, so they will be equal to each other. Log base 5 of 25 is equal to log base 25 divided by log of 25 divided by log of 5. So we can do the same thing with part B, where we want to evaluate log base 3 of 243. You can do this by writing it as an exponential function, starting with the base and cycling through. And again, we've seen that log base 3 of 243 is really asking 3 to what power is 243. This can be done by trial and error, finding out 3 to what power is 243. If we try 3 to the power 3, well, that's only 27. 3 to the power 4 is only 81, but 3 to the power 5 is 243. So x equals 5. And if you look at part 2, where you're asked to evaluate the log of 243 divided by the log of 3, for those logs, no base is indicated, which means it's base 10, which means, again, we can use a log function on our calculator. But once again, make sure you close the bracket after the 243. You actually don't have to close the bracket after the 3, because that is the last thing in the calculator, and we see that this also equals 5. So both of those expressions equal 5, so they must equal each other. And therefore log base 3 of 243 is equal to log of 243 divided by log of 3. They both equal 5, so they equal each other. What this leads us to is what's known as the change of base identity. You can evaluate any log with any base by using this identity. To evaluate log base 2 of 64, that can be evaluated using a calculator. We would say that log base 2 of 64 equals log 64 over log 2. The same pattern as we've seen above. And this is what the change of base identities tells us, that log base b of c equals log base a of c over log base a of b. Now, note that the base can be anything you want. 99% of the time, it's going to be base 10. A, the base, will be 10. The reason we use the change of base identity is so that we can evaluate it in our calculator. Okay? So the base can be anything we want. Normally it'll be base 10, so we can use our calculator to evaluate that. Now, some calculators with newer operating systems also have a log function built into them where you can input whatever base you want. All right? So to check to see if your calculator has it, you have to go alpha and then window for F2. Alpha and then window for F2. So if your calculator has F1, F2, F3, F4, F5 above these buttons at the top, it should have this function there. By going alpha and then hitting F2, notice that number 5 in this list is log with a base. So I choose number 5 and I can input a log with any base. Log base 5 of 25. So I hit the 5 and then I push the arrow to the right to get up to the next part, and it evaluates it. So for log base 3 of 243, it's alpha window. And again, if you have this function in your calculator, it's number 5 in the list. I put in a 3, then I use the arrow to go to the right, and then put in a 243. We get our answer of 5. Okay? If you don't have this function in your calculator, then you have to use the change of base identity, like we did earlier. All right? So we're asked to evaluate log base 4 of 1024. So this can be done 2 different ways now on your calculator. The first way would be using the change of base identity, which would be the log of 1024 divided by the log of 4. Note, whatever the base is, base 4, the log of that goes on the bottom. The argument, what you're taking the log of, goes on the top. So doing the change of base identity, it's a log of 1024, close the bracket, divided by the log of 4. And you get an answer of 5. If you have the newer operating system, alpha window, number 5 for log, put the base of 4 in there, use the arrow to go over to the argument, and that's where the 1024 goes, and you get the same answer of 5. Okay? Now, the second question, again, just uses the fact that when you use a change of base identity, you can use any base you want. Normally, you're going to use base 10, so you can just use your calculator on your log button. But it'll work no matter what the base is. So just to illustrate that, if I want to use the change of base identity to evaluate this, the numerator is log base 2 of 1024. Using the change of base identity, that's log of 1024 divided by log of 2. And that is divided by the denominator, which is log base 2 of 4. Again, using the change of base identity, it's log 4 over log 2. We're dividing a fraction. To divide a fraction, you multiply by the reciprocal. So the second fraction is flipped over, and you multiply instead of divide. So that'll be my next step. times the reciprocal, which is log 2 over log 4. And what happens here is that the log 2's cancel, and you'll get log of 1024 divided by log 4, which we got in part A when we just used the change of base identity. So again, this illustrates the fact that when you use a change of base identity, you can set the bases to anything you want as long as they're the same. If you do that, then those parts will always cancel. Okay. So example 3 says evaluate the following logs to the nearest hundredth by changing the base. So that means we're going to use the change of base identity. This will be the log of 221 over the log of 5. And the reason it says to the nearest hundredth is because in this case, our answer is going to be irrational. So we're going to have to round it to 2 decimal places. So using the change of base identity, it'll be the log of 221, close the bracket, divided by the log of 5. So again, it's an irrational number, so we'll have to round to 2 decimal places, approximately 3.35. And this could be checked if you have the newer operating system, alpha window, number 5, log base 5 of 221. Get the same answer. But we're told to do it by changing the base, so that's what we did. We used the change of base identity. Question B, that would be the log of 1 over 1,000. That's the argument divided by the log of the base, which is 2. So using the change of base identity, we get a negative answer. We said before that you cannot take the log of a negative number, and this change of base identity also illustrates why the base can't be negative either. Because if you change the base, use the change of base identity, it's divided by the log of the base. You can't take the log of a negative number, so the base can't be negative. But sometimes the answer is negative when you take the log. And when you think about what the graph of the log looked like, it went below the y-axis. It can't go to the left, it went below the x-axis. It can't go to the left of the y-axis though, which illustrates why you can't take the log of a negative number, because the graph had the y-axis as an asymptote. The graph was always on the right side of the y-axis. The only thing that would change that is if the graph shifts left or right. In this case, if it shifts left, then the graph could be to the left of the y-axis. But the graph does go below the x-axis, which means that y can be negative, and y is the answer. So the answer can be negative. In this case, it's negative 9.97 if we round to the nearest hundredth. Okay, now for question C, to use the change of base identity, it'll be 3 times the log of 512 all over the log of 7. Because 3 is the same as 3 over 1. You're not multiplying both top and bottom by 3, because if you did that, the 3's would cancel. Right? So it's just 3 over 1, which is why the 3 is multiplied by the log of 512. The log of 7 on the bottom is multiplied by 1. So that'll give us 3 times the log of 512, close the bracket, divided by the log of 7, which is approximately 9.62. And you can check that on the calculator if you have the newer operating system. 3, then alpha window, choose number 5, 3 log base 7 of 512. So there you go. Same answer. Just a little bit quicker if you have that newer button. Okay, so this next one's asks us to convert that with the base to the base 3. So that's just using the change of base identity. We've seen that when you do this, you can use any base you want. In this case, we're asked to write it with base 3. So it'll be log base 3 of 216 over log base 3 of 6. You normally wouldn't do this. The whole point of using the change of base identity so that you can use base 10 and therefore use the log button on the calculator. But as long as you keep the bases the same, you can write them with any base you want. So for question B, the base there is 10 because no base is indicated. If you want to write this with a base of 5, it'll be log base 5 of 300 over log base 5 of the original base of the original log, which is base 10. So there is the expression with base 5. Normally we wouldn't do that. The whole point of using the change of base identity is so that you can write it with the base 10 and therefore evaluate it on your calculator. So this says find the exact value of the following. So let's use the base, change of base identity and see what we get. Again, if you have the newer operating system, you can do it that way. If not, then you have to use a change of base identity like I've shown. So this will be log base 3 of 1 over 729. And there's your answer. Remember, you can get a negative answer when you take the log. You just can't take the log of a negative number. And the base can't be negative either. Okay? But this one works out to be exactly negative 6. Question B, if you use the change of base identity, it would be 2 times the log of 512 all over the log of 8. If you have the newer operating system, you can do it that way. You just have to put the 2 in first. So 2 times log base 8 of 512 is exactly positive 6. Right, question C, using the change of base identity, it would be the negative log of 1 over 343. So that negative in front is the same as multiplying by negative 1 or negative 1 over 1. So using the change of base identity would look like that. However, if you have the newer operating system, you can put it in there all in one step. You just got to put the negative in first. And then alpha window, number 5. Try that again. Alpha window, number 5 for the log. Whoops. Let me quit out of there. So alpha window, number 5. There we go. Log base 7 of 1 over 343. So the answer is positive 3 for this. Now the reason this works is because 7 to the 3 is actually 343. So if you did this manually, negative log base 7 of 1 over 343. If we want to know what this is equal to, we'd let it equal x. So this is asking 7 to what power is 1 over 343. But we have a negative sign here. So 7 to what power is 1 over 343. That's what it's really asking. But we have a negative sign here, so we'll make the 1 over 343 negative. Okay. 7 to the power x would equal negative 1 over 7 cubed. So 7 to the power x will equal negative 7 to the power negative 3. And so normally we would say that x equals negative 3, but because we have the negative sign there, that'll make that negative 3 a positive 3. And probably to do this, I should have divided both sides by -1 at the very start and made the x negative, and that would have been an x negative there, x negative there. Then I would have said negative x equals -3. That's how I should have done it. And that would have given me a value of x to be +3. So that would have given me the answer manually, but as we've seen, we can use our calculator. We don't have to do it manually anymore. That manual process is how we started it. Starting with the base and cycling through. Right? So question D, 5 to the power log base 5 of 25. What does that equal? Well, log base 5 of 25 is asking 5 to what power is 25? That's what log base 5 of 25 means. 5 to what power is 25? And that answer is 2. 5 squared is 25. That's the value of log base 5 of 25. And you can check that on your calculator. If you have the newer operating system, you can put that in. If not, use the change of base identity. Go log of 25 divided by log 5. You'll get 2. So the exponent becomes 2, and 5 squared is 25. So that's the final answer to that expression. Okay. Question E, we can do that using the calculator. It'll be log base 2 of the root of 1 over 1024. You get -5 as the answer. If you're going to do this one manually, if you want to know what log base 2 of the root of 1024 is, we would let it equal x. And then we convert from logarithmic to exponential. It would be 2 to the power x equals the root of 1024, which we can write as 1024 to the power a half. That's what square root means. I can make the bases the same by writing 1024 with a base of 2. I think that is 2 to the power 11, I think. No, it's 2 to the power 10. So I'm just using trial and error here. So that's 1 over 2 to the power 10 to the power a half. I can move the 2 to the power 10 from the bottom to the top by making the exponent negative. And now when you have one exponent raised to another, you multiply the exponents and keep the base the same. So now we've expressed both sides as a power with the same base of 2, so the exponents will be equal. So there's the answer manually, which is how we first learned how to handle these logs, by converting from logarithmic to exponential, starting with the base and cycling through. But now we can use our calculators. Okay, log base 7 of 49 to the -5. We can put that in our calculator. So if you have the newer operating system, you can go in just like it's written, 49 to the power -5. You get an answer of -10. Using the change of base identity, it would be log of 49 to the -5 over log 7. So again, by using the change of base identity, we would write it with a base of 10, so we can use our log button on our calculator. Just have to close the bracket after the 49 to the -5, and that's divided by the log of 7. We get the same answer. Okay. And it could be done manually by making it equal to x, write it in exponential form, and then solve the exponential equation. But we don't have to do all that work anymore. We can use the calculator. All right, so we'll come back to that. We'll be using the change of base identity more And then we're also going to learn about some laws of logarithms as well as we work our way through this chapter. So now let's look at transforming some logarithmic functions. So use transformations to sketch the graph of the function y equals log base 3 of x plus 9 plus 2. So this will be a transformation of log base 3 of x. So comparing it to log base 3 of x, you can see you've got those two other numbers added in there. You've got that plus 9 and the plus 2. Well, that x plus 9, that 9 is an h value. Remember, whatever happens to x minus h. But the value of h is the opposite of what it appears to be. So in this case here, we're going to have an h value of negative 9, which means the graph will shift 9 to the left. And we'll have a k value of positive 2, which means it'll also shift to up. Right? But this is a transformation of y equals log base 3 of x. So if we start with y equals log base 3 of x and we want to graph that, we can graph that by changing its form, writing it as an exponential function. Start with the base and cycle through. If we do that, that'll become 3 to the power y equals x. And we can graph that. We can graph that by using a table of values. The only thing is, now we would start with y values. Y is our independent variable. So we can let y equal negative 2, negative 1, 0, positive 1, and positive 2. When y is negative 2, 3 to the negative 2 is 1 over 3 squared, or 1/9. 3 to the negative 1 is 1 over 3 to the positive 1. 3 to the power 0 is 1, 3 to the 1 is 3, and 3 squared is 9. So I've got the point negative 2 comma 1/9. Sorry, 1/9 comma negative 2. I've got 1/3 comma negative 1. I've got 1 comma 0, 3 comma 1, and 9 comma 2. Remember, the graph of a logarithmic function like this one, if it hasn't been shifted left or right, the graph will have the y-axis as a vertical asymptote. So this is the graph of our base function. Y equals log base 3 of x. As the y-axis as an asymptote. So now we have to shift that to the left 9 units and up 2 units. So what that'll do is that'll make our vertical asymptote at x equals negative 9. Because everything shifts to the left 9 units. As well, everything goes up 2 units. So just as a point of reference to help us out here, let's just take a couple of key points from the original graph. And I'm going to use the points that had rational, or I should say integral values. So I've got the point 1 comma 0, I've got the point 3 comma 1, and I've got the point 9 comma 2. So if I shift those all, first 9 to the left, that means I'm going to subtract 9 from all the x values. So 1 take away 9 is negative 8. 3 take away 9 is negative 6. And 9 take away 9 is 0. I'm going to go up 2, so I'm going to add 2 to all the y values. 0 plus 2, 1 plus 2, and 2 plus 2. So I've got the point negative 8, comma 2. I've got the point negative 6, comma 3. And I've got the point 0, comma 4. So our new graph would look something like this. And we have arrows on the ends because the graph continues on in both directions. So there's the new graph. We're also asked to identify those characteristics. Equations of the asymptote, domain range, y-intercept if it exists, and x-intercept if it exists. So, part B, the first part is asking for the equation of the asymptote. Well, remember, it's a line. And an equation has a variable and it has an equal sign. The equation of the vertical asymptote is the line x equals negative 9. Then we're asked to state the domain and range. The domain of this will be from negative 9 to positive infinity. Neither are included. The range hasn't changed. It goes from negative infinity to positive infinity. We're also asked to state the y-intercept if it exists. And in this case, we actually got our y-intercept from a point that we generated. Our y-intercept is the point 0, comma 4. If we didn't, we could find it by letting x equal 0. So if we take our equation and let x equal 0, it'll be log base 3 of 9. 0 plus 9 is 9. Log base 3 of 9 is asking 3 to what power is 9? The answer to that is 2. 2 plus 2 equals 4. So we can get it algebraically, which is what we must do for the x-intercept. It does have an x-intercept. Our x-intercept is where y equals 0. So if we take that equation, it'll be where 0 equals log base 3 of x plus 9 plus 2. So we need to solve for x here. And we would do this by first subtracting the 2 from both sides. We want to get the log by itself. And I do that by subtracting 2 from both sides. And then once we have the log by itself, we can convert from logarithmic to exponential. We can start with the base and cycle through. So we'll get 3 to the negative 2 equals x plus 9. 3 to the negative 2 is 1 over 3 squared. 1 over 3 squared becomes 1 over 9. And now we will subtract 9 from both sides. So x will equal 1/9 take away 9, or 1/9 take away 81 over 9. 9 with the denominator of 9 would be 81 over 9, which is negative 80 over 9. That's our x-intercept. That's our value of x when y equals 0. Which is negative 8 and 8 over 9, almost negative 9, which is consistent with our graph. The x-intercept is almost at negative 9, just not quite. Okay? So this one will be a transformation of y equals log x. There is no base there, which means it's base 10. So if we are comparing to y equals log of x, We again have an h value in this case of positive 10, which means the graph will shift 10 to the right, and a k value of negative 1, which means it's going to shift 1 down. But we're starting with our base graph of y equals log of x. And again, no base is indicated, which means it's base 10. To graph this, let's write it as an exponential function. And actually, in this case here, we don't have to if we don't want to, because we can use our calculator. Right? And I could have done that on the previous example as well. We can use our calculator. Let x equal negative 2, negative 1, 0, 1, and 2. So using a calculator, if I want to know what the log of negative 2 is, well, I can't. Because remember, you can't take the log of a negative number. So we're going to have to adjust our table a little bit here, because you cannot take the log of a negative number. And you can't take the log of 0 either. The argument must be greater than 0. So maybe I will use positive 1/10, positive 1/2, positive, let's say, I don't know, 2/3. And now we'll use our calculator. The log of 1/10 is negative 1. The log of 1/2 is negative 0.3. So I have to use some estimating here. Log of 2/3 is negative 0.2. The log of 1 is 0. The log of 2 is positive 0.3. Let's do one more point here. Let's let x equal 10. It'll be helpful if we have a couple points that only have integral values. So all this is doing is helping us graph the base function y equals log x. When x is 1/10, y is negative 1. When x is 1/2, y is negative 0.3. When x is 2/3, y is negative 0.2. When x is 1, y is 0. I've got one point that I've got to move a little bit. There we go. When x is 2, y is 0.3. And when x is 10, y is 1. So we know that this graph will have the y-axis as the vertical asymptote. And we also see that raising the base just makes the graph a little flatter. Right? The previous example, we had a base of 3. This one has a base of 10. The graph is a little flatter. But now we're going to transform this. We're going to shift it 10 to the right. So now our vertical asymptote will be at y equals 10 and 1 down. So just to give us a couple points of reference, let's take the point 1, 0 and the point 10, 1. We're going to shift it 10 to the right, which means we're going to add 10 to both x values. That x value will become 11. This x value will become 20. It's going to go 1 down, so we're going to subtract 1 from the y values. So I've got the point 11, comma 1 and the point 20, comma 0. So we're going to have to kind of estimate where that is. Let me just check this again. 10 to the right. So I'm going to add 10. Oh, this should have been at negative 1. Because 20, comma 0 is approximately there. I just put this one in the wrong spot. It should have been 11, comma negative 1, not positive 1. There we go. So this is our new graph. So for part B, we're going to identify these characteristics, the first being the equation of the asymptote, which is the line x equals 10. It's an equation, so it has to have a variable, it has to have an equal sign. Again, we're asked to state the domain and range. The domain will go from positive 10 to positive infinity. Neither are included, so we need those round brackets, or rounded brackets. And the range hasn't changed. It goes from negative to positive infinity. Part 3, there is no y-intercept here. The graph doesn't cross the y-axis. And the reason for that is if you look at the equation and you let x equal 0, because that's normally how we find the y-intercept, if you let x equal 0, you're going to have the log of negative 10. You cannot take the log of a negative number. So that's why there is no y-intercept algebraically. Our x-intercept is where y is 0, which we have that point right here, 20, comma 0. But it could be found algebraically, which we've already seen how to do that. If you take that equation and let y equal 0, 0 will equal the log of x minus 10 minus 1. I would get the log by itself by adding 1 to both sides. Then I would convert from logarithmic to exponential. This log has a base of 10. If we start with the base and cycle through, it'll be 10 to the 1 equals x minus 10. And then when you add 10 to both sides, there you get your x equal 20. So had we not got the x-intercept just by luck, by what point we started with, and then when we did the transformations, it became 20, comma 0, you can still find it algebraically. Okay? So now we want to do this one. This is a transformation of y equals log base 2 of x. To get all my proper parameters, remember, to get the correct h value, b must be taken out as a common factor. We've seen that many times this year, or this semester. So if we compare it to log base 2 of x, and I just realized that I forgot to do the mapping notations for the previous one, so we'll make sure we do it for this one. If we compare it to y equals log base 2 of x, the first thing we see is that we have an a value of negative 1, which is going to reflect the graph about the x-axis. We have a b value of positive 2, which is going to cause a horizontal stretch. And remember, you must state that the stretch is about the y-axis. And so that stretch factor, remember, is always the reciprocal of b, which, because b is 2, the horizontal stretch factor is a factor of a half. And then x is replaced with x plus 3, which means our h value is negative 3. So this graph will also shift 3 left. But this is a transformation of y equals log base 2 of x. So for y equals log base 2 of x, we're going to get a table of values for this. And we can get it using our calculator or just using some logic, right? Whatever we put in for x here, we want to know 2 to what power will equal that value of x. Okay, Josh? You with us? Good. So x must be something that we can write 2 to some power to equal that number. Okay, so I can let x equal a half. When x is a half, 2 to what power is a half? Well, 2 to the negative 1 will give us a half. I can let x equal 1. 2 to what power equals 1? Well, anything to the power 0 equals 1. I can let x equal 2. 2 to what power equals 2? 2 to the 1 equals 2. And I can let x equal 4. 2 to what power equals 4? Well, 2 to the power 2 equals 4. I can do one more if I want. Let x equal 8, because 2 cubed equals 8. So these are points on our original graph. I got the point 1 half comma, negative 1, 1 comma, 0, 2 comma, 1, 4 comma, 2, and 8 comma, 3. Remember that unless the graph has been shifted left or right, the y-axis is an asymptote. Remember we said earlier too, as the base gets larger, the graph gets flatter. Here the base got smaller. It's log base 2 of x, so it's not as flat as log base 10 of x. So there's our graph. And now we have to do these transformations. Okay, so just to keep everything straight, let's start with the original points that we got here. And let's deal with each parameter one by one. The first one being our a value is negative 1. Remember, we've learned that you always do your stretches and reflections first, do your translations last. If you do them the order they're written in the equation, as long as y is by itself, then you'll do them in the proper order. So the first one being that a is negative 1, that causes a reflection over the x-axis. All the y values will get multiplied by negative 1. So our x values will stay the same. Our y values will get multiplied by negative 1. Next, we have a b value of 2, which causes a horizontal stretch by a half. All the x values are now multiplied by a half. So in this step, the y values won't change. The x values are multiplied by a half. And our final step is our h value of negative 3. That shifts it 3 to the left. So we are going to subtract 3 from our x value. So 1/4 take away 3 would be 1/4, take away 12 quarters. 1 minus 12 is negative 11 quarters. 1/2, take away 3 would be 1/2, take away 6 halves. 1 take away 6 is negative 5 halves. 1 take away 3 is negative 2. 2 take away 3 is negative 1. And 4 take away 3 is positive 1. So everything shifted 3 to the left, which means our vertical asymptote will now be at x equals negative 3, because it shifted 3 to the left. We can put these other points on there. The point negative 11 quarters, which is negative 2 3/4, comma 1. Negative 5 halves, negative 2.5, comma 0. Negative 2, comma negative 1. Remember, this graph reflected over the x-axis. Negative 1, negative 2, and 1, comma negative 3. I'm going to use a different color here when I actually draw the graph. So there's our new graph. Again, this one was reflected over the x-axis. That's why it looks this way. Okay? So now we're going to state the characteristics. First being the equation of the vertical asymptote, which we said was x equals negative 3. Our domain will be from negative 3 to positive infinity. Neither are included. Our range still goes up and down forever. Number 3, there is a y-intercept. That's where x is 0. We don't have it on our table, so we can find it algebraically. Our y-intercept is where x equals 0. So if we take the original equation, it'll be y equals negative log base 2. When you let x equal 0, you're going to get 2 times 0, which is 0, plus 6. It'll be negative log base 2 of 6. This is going to be an irrational number, which we can get on our calculator. Have to put the negative sign in first, then log base 2 of 6. So it's at approximately negative 2.58. Or the point 0, comma, negative 2.58. Our x-intercept is where y equals 0. And in this case, we actually have it in our table. That is the point 1, comma, actually, no, we don't. Yeah, we do. Negative 5 halves, comma 0. But as we've seen, we can do it algebraically as well, which we've done. We let y equal 0 and solve for x. So we also want to find our mapping notation. So the x-intercept was part 4. Part 5 is the mapping notation. So the ones that will affect the x will only be the horizontal stretch and the shifting 3 to the left. Horizontal stretching by a half. And remember, mapping notation has to start with x, comma, y. Then you have an arrow which represents maps into. So we have a horizontal stretch by a factor of a half, so the x values are multiplied by a half, and then they were decreased by 3 to go 3 to the left. The y values were multiplied by -1 because we have our reflection over the x-axis. So there's the mapping notation. 1/2 x take away 3, comma, -y. But you have to have the x, comma, y first. That's always part of it. Okay? So looking at this last one, again, one of the steps we've always done is taking b out as a common factor. A b value is -1. Taken out as a common factor will give us x minus 1 inside the bracket. To get the true h value, we've always done this, taking b out as a common factor. Okay, Blanny? So if we're going to compare this to y equals log base 3 of x, the first thing is we've got an a value of +2, which will cause what, Josh? But it's vertical stretch about the x-axis. By a factor of 2. Then we have a b value of -1, which is going to cause a reflection about the y-axis. And then we have an h value of -1, which means the graph is going to shift 1 left. And you might find it easier to do the mapping notation first. So reflecting it about the y-axis means that the x values will be multiplied by -1, and then we're going to shift 1 left. So after multiplying by -1, you're going to subtract by 1. The vertical stretch by a factor of 2 means that the y values are multiplied by 2. So if we wrote the mapping notation first, that's what it'll look like. And if you do this, then really you only have to find points on the original graph, and then you can apply the mapping notation to get our new points. So let's generate some points on the original graph. If we want to get some points for this, we want to find out what y equals for different values of x using log base 3 of x. Now remember, whatever you put in for x, you're saying 3 to what power equals x. Okay, so if x is a third, well, 3 to the power -1 would equal a third. When x is 1, 3 to the power 0 will equal 1. When x is 3, 3 to the power 1 equals 3. And when x is 9, 3 to the power 2 equals 9. So those are points on the original graph. 1/3, -1, 1, 0, 3, 1, and 9, 2. The original graph, again, would have the y-axis as our vertical asymptote. Our new one, because it shifted 1 to the left, will have the line x equals -1 as our vertical asymptote. And again, to get our new points, let's take the original points And we'll just do one step using our mapping notation to get our new points. Being the x values are multiplied by -1, so you're going to get -1/3. Take away 1, we can just write that as -1 1/3 if we want, instead of getting a common denominator for the 1. 1 times -1 is -1. Take away 1 will give us -2. 3 times -1 is -3. Take away 1 is -4. And 9 times -1 is -9. Take away 1 will be -10. Remember, this graph is reflected over the y-axis. That's why the x values are getting smaller. This graph is going to be to the left of our vertical asymptote. Our y values are just multiplied by 2. So I've got the point -1 1/3, comma, -1. I've got the point -2, comma, 0. -4, that should be +2, not -2. You're multiplying the y values by +2, not -2. So -4, comma, 2, and -10, comma, 4. So there's our new graph. The equation of the asymptote, again, is the line x equals -1. Our domain and range are going to change here. Well, our domain specifically. This will go from -infinity up to -1. Neither are included. Our range doesn't change. It still goes from negative to +infinity. There is no y-intercept. The graph is always on the left side of the y-axis. Remember, the y-intercept is where x is 0, and if you take the original equation and let x equals 0, it'll be log base 3 of 1 times 2. I'm sorry, I made a mistake here. I apologize. That does exist because it doesn't go 1 to the left, it goes 1 to the right. So I really apologize for that. There is a y-intercept. This graph goes 1 to the right. So I've got some things to fix here. The mapping notation will be -x plus 1 because it goes 1 to the right. So that's going to change all these x values as well as my asymptote. So again, I apologize for that. -1 times 1/3 is -1/3, but then we're going to add 1, which will be +2/3. 1 times -1 is -1, plus 1 is 0. -3 plus 1 is -2. And -9 plus 1 is -8. So when we look at our graph, the asymptote is at +1. And these points are all going to move one to the left. So the graph is going to go one to the left because all these points go one to the left. And actually, some are going to be more than one to the left because you're multiplying by -1 first and then going one to the left. So there is a y-intercept. Our vertical asymptote will be at x equals +1, not -1. Our y-intercept is where x equals 0. So this is how I knew I made a mistake, because the y-intercept does exist. If you let x equals 0 here, it'll be y equals log base 3 of 1, 2 times log base 3 of 1. Now, it's actually in our table because the log of 1 is always 0, doesn't matter what the base is, and 2 times 0 is 0. Sorry? Yep, got to fix that too. But this is your x and y intercept. It equals 0 as well. So it also equals the x-intercept as well. And yes, our domain will go to +1, not -1. Okay, so again, sorry for that. We already did our mapping notation down here. Right? We used it to generate our points. Okay, so for practice, you should be working on these questions. I will post the solutions to Google Classroom for you to check your answers. There is some graph paper up here if you want to help you do some of those graphs.